Started. I believe where we ended was looking at the curved arrow notation. We can use balance reactions, all sorts of fun stuff, find where everything is, right? Is that where we ended?
Yeah.
Okay. So when we're thinking about curved arrow notation, what we're using is the exact same rules that we used for resonance. Okay? It's the same kind of a concept, the same kind of idea. That's why we talked about resonance at the beginning. Okay? And for those of you thinking that resonance wasn't that big of a deal, here it's showing up again. You have to know curved arrows. You have to be able to use them to explain how a structure reacts. Okay? So if we think about resonance, we find our source of electrons, which is either our pi bonds or lone pairs. Right? We move them from atom to bond or bond to atom. Remember, we have the last kind of option in there. Bond to bond. Okay? And it's from one bond to an immediate bond next to it. We're not jumping across multiple parts of the structure. Okay? We would verify that our octet was satisfied. If not, we'd break a pi bond by moving electrons away from them. So if we looked at the structure below, we could try and draw out resonance for it. Right? Which electrons should we attempt to move in that structure? Why the ones on the carbon? Okay, so if we go through and look at it, we've got the lone pair on the carbon, we have the lone pair on the oxygen, 2 lone pairs there, and we have that pi bond. So there's 3 potential sources of electrons we could move, okay, when dealing with resonance. Felicia's suggestion was by far the best. When we go through and look at that, we need to pick the most reactive electrons to move. Why are the ones on the carbon the most reactive? They're making the carbon negatively charged. That's why we should start with those. So what we would do is try and move those from an atom to a bond and see what happens. If I tried to move them to that bond, what would the resulting structure look like? Right? I've changed nothing else about the structure. I've just moved the pi bond over. And we might say, well, that looks like a valid resonance structure. Except did you potentially forget the fact that every line ends in a carbon, and that carbon must have an octet? And if I only see one bond, there's 3 hydrogens there, which then means the resulting structure I've drawn exceeds the octet. In resonance, that's kind of okay. If it is not, I have to break a pi bond moving away. Okay? So this structure is invalid, but I can use that to help me fix my instructions on the previous structure. So I look at it and say, well, my octet has been exceeded here. I need to move a pi bond away from it. Where's there a pi bond? Where's there a pi bond on that carbon? That carbon is my problem. I don't care about the pi bond with the oxygen because it's not connected to the exceeded octet.
The one you just drew.
The one I just drew is the one I need to focus on. It's not just looking for a pi bond somewhere in the structure. Okay? We need to find the one that's causing the issue. The issue is that immediate pi bond, which means that pi bond has to move away from it. Okay? Because it's a bond, I can only move it to an atom. It has to move back. Okay? Remember, this structure is invalid, but I can still use that as my guide to do the arrow I've put over here. I also have to include the green arrow in that same drawing. What's the result of that arrow pushing now?
No net movement.
Okay. If we draw it all out, there's my 3 hydrogens. I put the pi bond or the lone pair immediately back onto the carbon. I can evaluate charges, and I end up with the exact same structure I started with, which means, was that red arrow a good direction to move? No. Okay? When we talked about resonance, I told you to do that at the beginning of the semester. I wanted you to see that that is a problem. Draw that invalid structure and be like, well, how could I fix it? Okay? We re-add that information back on our initial structure that is valid, and now we can draw out the result. The end result is, well, that was pretty crappy. I can't do that. Okay? So, where else could I have moved that lone pair?
The bond with the nitrogen.
Okay? I could move it to the bond with the nitrogen. Based off of that single arrow pushing, what would the result be? Okay? I exceed the octet on that nitrogen. Okay? And again, I'm okay with you acknowledging that and drawing this and being like, oh my God, that's a horrible thing. Okay, yes, it is a horrible thing. I'm not allowed to say that structure exists. I can show that as work to allow me to think about what's the next move. The nitrogen has exceeded its octet. According to resonance, what do I have to do? I break a pi bond. What is special about this nitrogen in comparison to the carbon we had before? There's 2 pi bonds. I could break the pi bond that I just formed. As we just saw, if we did that, that takes us backwards. Okay, so let's break the other pi bond. Where should those pi electrons go? They need to go away from the nitrogen. Adding that curved arrow on this structure isn't inherently bad, but I'm adding instructions on a structure I'm not allowed to draw. Okay? So I can take that information and include that arrow on the structure that was valid. Okay? Now I can ignore that bad structure, and I can draw the results of my arrow pushing. What do I get? Yes? No?
Well, you now need to do formal charge.
Yes, now we do formal charge. Okay? And watching students go through and do these things, you tend to include formal charge first. No, formal charge is the last step of Lewis structure. Show where the electrons move. Now you can evaluate formal charge. When we go through and evaluate that formal charge, there's 2 ways to go through and do it. 1, do it like we did at the beginning. Painfully count out valence electrons, minus bonds, minus non-bonds, and do all that fun stuff. Or 2, assume the structure we started with had it correct and evaluate what the arrows show. If we take a look at the carbon, it started negative. What does the arrow show? It lost electrons. So if we're negative and I now lose electrons, it's more positive. It goes to a neutral state. So no charge on the carbon. Nitrogen started positive. It's got a bunch of arrows going around it, so that could be challenging. Do you want to look at that one first or the oxygen? Okay, well, we'll start there. What happened to the nitrogen? Nothing happened to it. Arrows came towards it, which means it gained electrons. And arrows went away from it, which means it lost electrons. What's the net result? Nothing. So what should happen to its charge? It stays the same. What happened to the oxygen? Bless you. It gained electrons. Electrons were moved towards it. If it gains electrons, it needs to become negative. So one option, we calculate all the formal charge, right? Painfully. Second option, we use the meaning of the arrows to help us evaluate it. There's a third option. Remember in Unit 1 I said there's common bonding patterns and you need to know these common bonding patterns, that's like the lesson of Lewis structure, is so that you've got those common bonding patterns memorized. Right? If you don't remember me saying that, go back and watch the lectures. You should probably go back and watch lectures anyway. I mean, it's exciting stuff. Right? I said that multiple times. And if we go through and evaluate that, we will find that an oxygen with 3 non-bonding pairs and a bond is negatively charged. A nitrogen with 4 bonds is positively charged. A carbon with 4 bonds is neutral. If I had those things memorized, I've got my charges immediately drawn on it without having to think about and process things. Okay? It's just a question of where you want to spend time thinking about processing that knowledge. Make sense? Okay. So that was resonance. Nice little quick resonance review. Okay. In a mechanism, we're going to do something similar. We're going to find a source of electrons. Typically, that source of electrons is lone pairs or pi bonds, but it does not have to be. Right? It can sometimes also be a sigma bond. Right? And we're allowed to do that in a reaction because in a reaction, we are literally breaking and making sigma bonds. So I'm allowed to do that. So if I look at that starting structure, right, I have lone pairs, right? I could move those lone pairs. I have pi bonds. I could move those pi bonds. Right? And I could evaluate what the end result would be. Or I could break sigma bonds. What do you guys want to take a swing at? Just breaking a sigma bond. Which sigma bond do you want to break? Pause. How many sigma bonds are in that structure? We have all of the hydrogens in there as well. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Because there's another hydrogen in here. Right? Which of those bonds is most likely to break as a sigma bond?
The bromine-chlorine bond because of the electronegativity.
Bromine. Okay, yeah, sorry. I was looking at it the opposite direction too, which made it even worse. The carbon-bromine bond is likely to be the easiest one to break because it's electronegative. So what we're looking for is a difference in electronegativity because that's going to highlight reactivity. Right? That bond is very likely to break. And it is very likely to break with the electrons going where? To the bromine. Why? Bromine's more electronegative. Right? What would the result of that single arrow pushing be? Right? I broke a sigma bond. Right? So if we got a little bit more careful here, I would have ended up with something that looked along these lines. This gets extra dangerous. Okay, whoops. And it gets extra dangerous because I have to account for charges now when I go through and approach this. What happened to the bromine? It gained electrons, which means it's negative. 9 times out of 10, students get the negative charge spot on correct. Fantastic. What do students tend to miss? The carbocation. Because when you look at that, what charge does that carbon appear to be? It looks neutral because we go, well, it's got 2 bonds, so that must mean there's 2 hydrogens attached to it, so it must be neutral. In the previous structure that it came from, how many hydrogens were attached to it? 1, which means one of those hydrogens is false. Okay? With that extra hydrogen drawn on there, now we can go back to our memorization aspect. Oh, there's a carbon with 3 bonds. That must mean positive. Okay? Or if we go back and heavily evaluate and use the instructions that we've included on this, we would also notice that the carbon lost electrons by that arrow pushing, and thereby the carbon becomes positive. Make sense? That positive charge is a very easy one to lose. So when you go through and run a reaction and you don't see a positive charge, you should probably take a quick 30 seconds to go back through and reevaluate that because you probably missed something. Not a guarantee, okay, but it is a high likelihood that you missed something there. Okay? At that point, we would now evaluate a new structure and say, well, what could possibly happen here? Okay? Well, I've got a negative bromine and I have a positive carbon. Are those things stable? No, why not? They're charged, so I would ultimately want to stabilize them. How could I stabilize them? Okay, I could form a bond, which would mean I would need arrows. I would need electrons so that I could show the motion of those electrons, and I could do something like that. That was horribly aimed. Let's try that again. Okay. That takes me backwards. Well, that was kind of boring. Okay. So maybe there's something else that could happen. There's another negative in solution. That other negative could attack. Why would that other negative be more likely to attack than the bromine or bromide?
Because it's less electronegative than bromine.
When we compare those negative charges, we're looking at a negative carbon or a negative bromine. Bromine, being more electronegative than carbon, holds the electrons tighter, which means, given the choice, bromine's not going to share. That means carbon should share them instead. So we can use electronegativity here. Okay? There's another aspect that we should be considering that's actually more important. It's not electronegativity. Size. Bromine is significantly larger than the carbon. We've never talked about size before. Remember back through Unit 1, second lecture, even before we talked about memorizing the bonding patterns, it was like we've got our periodic table and there's trends on the periodic table. And there were two trends that I said were really important that you needed to know. Size and electronegativity. This is why it becomes important. We have to be able to look at those atoms as they're drawn, and they apparently look the same size. We have to be able to process that those symbols are not drawn to scale. We have to know that size difference is there. How does that size change the reactivity? There's bromine. There's carbon. What made each of those reactive? The negative charge. What makes it negative? An electron. How many electrons? Too many. Is that really what you said? That's a pretty solid answer. One. Only one electron. So there's one electron. What is the size of one electron in one atom versus another?
It's the same.
It's the same. So there's my one electron. Okay, so now we can look at those two pictures for a moment here. And we'll take a minute because I did see a hand. What do you got, David?
I was going to say you should draw a little smiley face because then we won't have to eyes.
The electron is what makes those unstable. Have we seen electrons somewhere else in the world around us? Electricity, okay? And those are in like outlets put against the walls, and we're told from very young ages that we don't stick our fingers in them, right? Why?
Because then electrons will flow into you.
Electrons flow into it. So electrons are dangerous things. We don't want to touch them. Which of those is more stable? Well, that's kind of hard to say. For it to react, something must encounter the electron. Let's make that something your hand. You have to stick your hand into those individual circles. Which one are you going to stick your hand in?
Bromine.
Why are you going to stick your hand in the bromine?
Because there's a much higher opportunity to not touch the electron.
You're probably not going to touch the electron in the larger atom. You've taken that electron and dispersed it across a larger area, which means it is less likely to react. You're not going to stick your hand in the carbon because you're probably going to touch it, and that's going to hurt. Okay? Same thing is happening when we look at the reactivity of these things on that nanoscale level. Okay? So size becomes very important for that reactivity. Okay? Make sense? It's neat. You just got to use it now like hundreds of thousands of times, and you've got OChem. Okay? Questions? Okay. My question. Give you a couple minutes. We've got 5 questions here. Which is the strongest acid? All you got to do is identify it. Oh, that sucks. Okay, let's go. Let's start up at the top. We'll just do left, right. So we'll go 1, 2, 3, 4, 5. So each one left or right. So starting with 1.
Left.
2.
Right.
3.
Right.
4.
Oh, sorry, no. For 3's left. Sorry, I got them mixed up. And then
Actually, hold on a sec. 4,
Right.
5.
Right.
One of those is a different color. Why might that be? Dang it.
That's close.
That was really good. Formulas are dangerous to evaluate. If we draw out the structure, you want to change your answer? And of course you want to change your answer.
Yeah.
Why would that now change your answer? And don't tell me, well, because you said I was wrong. That doesn't count.
It's because the oxygen is comfortable being negative. And the one
You're telling me water doesn't have an oxygen that's
Well,
comfortable
no,
being
but
negative?
Okay. It's a good counterpoint.
No, that's cool. So hold it for a second.
Yeah.
What do we got?
I would say that because there's just the electron density shifts towards the oxygens. So you've got the oxygen with the double bond, which is pulling the electrons away from the carbon. So the carbon is a little bit more electron poor. So it wants to hold on to the carbon oxygen single bonds slightly more than normal, which means that oxygen, in order to be the most comfortable, yes, that way. It's basically, and then that makes it weak enough that something can.
So that explanation is, if we go through and look at that, we've got that second oxygen drawing electron density away from the carbon, which then makes the carbon unhappy, so it draws electron density away from the oxygen, which makes it unhappy, so it draws electron density away from the hydrogen, which then means hydrogen floats off and becomes the acid. Okay? That explanation is what is fancily known as induction. Okay? Could we use a hybridization effect to describe this? Yeah, it's a little bit harder, a little bit less tenuous to do, but I would argue both of those are ultimately going to be wrong. Okay? As explanations. Okay? There's one really big explanation that you guys should have nailed right away. So it's kind of cool that you were looking at like deep details of how those possible electronic things can look at. And Christian's laughing because I already made fun of him for this in office hours. Why are you laughing?
It's a carboxylic acid.
It's a carboxylic what? The functional group is literally called an acid. Which one do you think is more acidic? The one we call an acid or the one we don't call an acid? Okay? So feel free to take advantage of other pieces of information to stack into this. Okay? The reason we point this, or I run through this, is that what we're asking you to do is think about different explanations for why each of these is more acidic or less acidic than the other. Okay? That reasoning and that logic is not something that's given to you in Gen Chem very well. Okay? And if I remember correctly, this is largely what you were given in Gen Chem. Okay? At least if you were taught out of the, I believe it's the Brown, LeMay, Burston book. Okay? Down a column, stronger acids have larger conjugate bases. So when we go back to look at, say, these two, chlorine versus fluorine, which one's larger? Chlorine. So down a column, when we compare those two, it's fluorine versus chlorine. Down a column, the larger one is the stronger acid. Sweet. Right? Oh, man. Across a row, stronger acids have higher electronegativity. So if we doubled back and compared over here, H2O to HF, right? It's oxygen versus fluorine. Across that row, fluorine is more electronegative, so HF is the stronger acid. You got H3O plus and H2O right. That was neither of those rules. How'd you do that?
Well, I knew that it wanted to give away hydrogen
Why?
because it wants to be neutral.
Yes. We're evaluating charge in that first one. H3O plus doesn't want to be charged. If we looked at a Lewis structure for that, we'd have a positive oxygen. Oxygen doesn't want to be positive. So what does it do? It steals electrons from one of the hydrogens. Okay? If we look at water, it wasn't charged to begin with. So there's not a huge driving force for it to want to get rid of that hydrogen. Okay? Another way to look at it, hydronium ion, like you spent most of 152 talking about hydronium ion, which was a result of it being an acid. Yeah, okay. So H3O plus, you should be triggering on it being an acid. You could look at the charge. That's fantastic. That's awesome. That's next level stuff. That's OChem. Right? When we move into H2O versus formic acid, don't stress about the name. Okay? The evaluation there, you were digging deeper. Because when we evaluate, was there a size difference? Okay, if we look at the conjugate base, I see some people being like, yeah, there totally was a size difference. What's the size difference we're referencing?
You're talking about like the entire.
I'm not talking about anything yet. I'm just asking about the size difference. Is it the entire molecule?
No, just the atom.
Just the atom. Fluorine versus chlorine. When we go down to this one, what's the atom? Oxygen versus oxygen. Is there a size difference?
No.
No. We can't use the size explanation. There was no charge explanation. Okay? Well, that's because there's a difference in electronegativity between oxygen and oxygen. Ooh. How can I explain that difference? Okay, well, our cheat was, well, that's a carboxylic acid, dude. It's an acid, that's why. We called it an acid because of its reactivity. We can't now backtrack and say that's the explanation. So why is the negative charge more stable on this oxygen in formic acid than it is in the hydroxide? Resonance. The electrons can donate into the structure so that when I draw out a resonance compound for this, what happens to the charge on our original oxygen? It neutralizes, which means the effective charge for this molecule is -0.5. Whereas for water, or the hydroxide ion, it is -1. Which one's more stable? The -0.5. Resonance is allowing us to explain the acidity. Okay? Yes, we can evaluate induction. It turns out that inductive effect, that electronegativity effect, is a smaller effect than resonance. Okay? Why? In resonance, what are you doing? Moving electrons. In the inductive effect, what are we doing? We're just saying electrons are kind of like not sharing as evenly. Are we actually moving them? No, we're just saying they're just leaning one way. Resonance is they move. Induction is they lean. Which one's the stronger effect? Resonance. When we move to the last one, now we can full on use an inductive effect. There is no resonance effect. There is no size effect. Okay? The reason why CH3F is a stronger acid is that fluorine withdraws electrons from the carbon, which then withdraws electrons from the hydrogen. Okay? If we go back and look at all the rules that you potentially learned, the first two are there. That's cool. Rule 3, which I always found irritating, HOX becomes more acidic with a higher X electronegativity. This is so nuanced into one particular structure that it becomes a useless rule in OChem. We can't apply that to anything. Okay? Rule 4, HOXON becomes more acidic when we have a larger N. Yeah. Okay. What are those rules referencing? Which of those is the stronger acid? The chlorine one. Why? Don't tell me rule frickin' 3. When we remove the hydrogen, what happens? We have that negative oxygen, right? Down a column, it's still oxygen. Rule 2, still oxygen. What's the difference? What it's attached to, chlorine versus bromine. What's the difference between chlorine and bromine? So we could evaluate size if that size was directly affecting the negative. It's not affecting the negative anymore because that's not where the negative is held. Electronegativity. Chlorine being more electronegative does what to the electrons in that bond? It takes them a little bit tighter, which then means the oxygen becomes more stable. Rule 3. You increase the electronegativity of atom X, there it is. It's an inductive effect. What is rule 4? I'll leave that for you to prove yourself, is a resonance effect. Okay? I'm a bit irritated at this because the order of those two rules is inversed. Resonance is more important than induction. Okay? Ultimately, when deciding acidity, okay, or really the stability of anything, you're trying to minimize charge. That's your bottom line rule. Okay? After that, it's how do you apply that rule? It's helpful to draw out a reaction, to look at structures, to apply it and think about it. If we're looking at acids, we typically evaluate the conjugate base. Why would I look at a conjugate base to evaluate an acid?
Isn't it the weaker conjugate base the stronger the acid?
Yep. Why would I evaluate the conjugate base? There's my acid. Why is it easier for me to look at the conjugate base? There's the conjugate base, right? Why is it easier for me to look at the conjugate base than to look at the acid?
You don't see the hydrogen.
You can
Not
look at
hydrogen.
resonance, you can look at all sorts of things. Now I know.
Why can I look at resonance? Yes.
Because I know where the negative is located. I know which hydrogen went away.
The negative is located. I can see the electrons. The conjugate base shows me the electrons. That's why I look at the conjugate base. I can see the things, okay, that dictate all of organic chemistry. When I look at the acid structure, I can't see those things. That makes it more difficult to evaluate. So I focus on the conjugate base. What happens when we go through and look at base strength, though? In bases, we just say evaluate the most negative. Why all of a sudden am I switching? Because if I drew out a base here, why do I not look at the conjugate acid? What does the base need to start with? Not necessarily a negative charge, but getting down the right idea. Electrons. What do I move in OChem? Electrons. For bases, I evaluate the starting structure because all of the rules that I use to define how organic chemistry work start on that structure. Acids, I look at the conjugate base because all of the rules that I use to explain reactivity in organic chemistry aren't obvious in the starting acid. I have to draw the conjugate base. Okay? This becomes tricky because now we're changing our focus between these. And it's only tricky because you go through and memorize and go, oh, I always need to look at the conjugate partner. No, you don't. You need to memorize what the rule is that you're being asked to compare on. If I'm asking you to look at acids, okay, the reactivity is going to change than when I ask you to look at bases. Why would that be? Why does the reactivity change if I ask you to look at an acid versus a base? Damn, that's a hard question. Define an acid. That is not a hard question. You should have that by now. A hydrogen donor. Define a base. Are their definitions the same? No. Why do our rules for explaining ranking of acids and bases differ? Because they're different things. You have to use a different rule set to explain it. That's it. That's all it is. Right? You have to know the definition by which you're placing all of your rules. The rules themselves don't change. It's still stability. You're going to minimize charge. Okay? When I look at an acid, the whole point is that I minimize that negative charge. Why do I want to minimize that negative charge to be a strong acid? If this is more stable, what happens? The reaction happens. In which case, what do I produce? H+, which would be acid. Okay? When I look at the base, do I want to minimize the charge on the base? Why not?
Because it's a base. It's different than acid.
What is the base trying to do? Accept a hydrogen by
Gain electrons?
donating the electrons. If I know the definitions, it's just a question of applying the definitions of stability back to these, to each of those individual reactions. That takes practice. When we think about OChem, usually when we talk about acids and bases, OChem 1 is all about ranking acids. You will see ranking of acids up the yin-yang on the ACS. You probably won't see questions ranking bases. Okay, why? I don't know why. Because it's the same freaking system. They shouldn't flip it. But they, for whatever reason, decided that base strength is something that should be talked about in second semester. It's the exact same rule set. And by dividing them up like that, guess what happens? You do great at ranking acids, and then we move to bases, and what happens? You fail miserably at it because all you've done is ranked acids, so that's all you try to apply. Right? Realize they're the same thing, just different sides of the coin. Okay? So what would be a better rule set to go through and look at this as? Okay? We'll almost look at that. Okay? Our rules. The very first thing you should look for would be charge. Do I want atoms to be charged? No. Okay? So atoms are always going to try to minimize charge. So the first thing I want to look for is see if there is charge. Because if there is charge, that I can now apply to my acids and base definitions very quickly and efficiently. Okay? The next thing I want to look at is an atom effect as well. I want to look at the size of the atom. Okay? Because if the atom is really big, what is it going to do to that negative charge? It's going to stabilize it. The next thing I'll look at is electronegativity. It's, again, an atom effect. Okay? The next thing we'll move to is what I would call a molecular effect. We've gone beyond the atom now. We've done all the comparisons that we can make at a simple level for looking at the atom. So now we've got to say, does the molecule have an effect? Okay? Which is true. If we think about what you need to do when you go through the homework, what do? It's the first thing you do with the homework. Oh, crap?
Is it high?
It's about the same. Cry. How? So you just start crying right now. When do you start crying with the homework? When you opened it up and you looked at it, right? And then you started crying. Why? Because you checked your brain and you're like, I don't know the answer. Okay? Maybe you didn't start crying. Why did you not start crying? I knew the answer. Okay? What happens then? You've cried. Oh my God. This is a fun thing for life. If that's now the end of it, what happens?
Failure.
It sucks. You fail. That shouldn't be the end of it. Okay? Right now, I think that is all too common. That is the end of it for a lot of people. Okay? What should you do after that? God, I don't know what to do after that. Some of you do.
Keep trying.
You could keep trying. You could go back to the homework or the textbook. Cool. Okay? All of that is internal. That's you. What could you do? You could ask for help. You could reach out to your support network. You could reach out to the people on the outside. If you don't have that support network, that becomes very difficult to get through the class. Right? That's one of the things we're trying to build, is you coming and talking to me, you coming to talk to your friends. That's that molecular effect. That is that secondary support network. Right? We look at that effect. What happens if we exhaust all the molecular effects? Yeah, it was about right. Okay. I don't know why I did it that way, and I get made fun of for it every semester. But O-carp. Right? Really what happens at that point is we now move into the subtle nuances of stability. This looks at hybridization. This looks at substitution patterns. Those are much more difficult concepts to deal with and to apply at this scale. That's why it's an crap moment. Okay? Because it is a lot more difficult to evaluate that. Right? Thankfully, how often do we encounter that? Close to never. How often do we encounter all the other ones? Like all the time. Every single question you encounter, will involve all the others. Okay? I cannot stress this enough. Every single question is asking you to look at those other things. Okay? It may not be obvious, but that's what it's asking you to do. You have to push to that level. Okay? Which puts us to our first question. Okay? We got two sides of the classroom, 2 questions here. Who wants to do which?
I'll open that side.
So you want to do this one?
Yes.
Okay, so everybody on this side of the classroom gets to do that red structure there. Everybody on this side of the classroom gets to do the non-circled one, which I'll go ahead and put a box around it. Okay? I want to know the most acidic hydrogen in each of the 2 molecules, and then specify which of those 2 compounds is the most acidic. This is fun. You get to find the most acidic one, and then you have to do the other side of the classroom's work also, so you can do a comparison. Okay? Because you aren't moving fast enough. We'll make. Admittedly, it was a little bit nice because nobody was fully evaluating it. When we go through and look at that structure, everybody did a pretty decent job of comparing the oxygen hydrogen to the carbon hydrogens. There's actually more than just the oxygen hydrogen and the carbon hydrogen. This purple hydrogen is more acidic than the red hydrogen. Okay. So there are explanations behind that. You need to dig at those explanations. Okay. The same thing is going to happen on the other side. Okay. I got people referencing the oxygen hydrogen, and I got people referencing the carbon hydrogen. Same issue, you still have that purple hydrogen, which is going to be more acidic than the red hydrogen. Okay? So you should be considering that and evaluating that. Ultimately, that's not the biggest answer. So when we go through and look at it blue to red, blue is more acidic than red. Because oxygen is more electronegative than carbon. It has nothing to do with necessarily anything else. You have to make that comparison. It's not just that it's more closer to an electronegative element, it's that it's connected to oxygen versus carbon. Okay? In that comparison, the oxygen is more electronegative than the carbon, and that explains it. Okay? The charges end up coming out the same. One of the common answers that came out of this was oxygen is bigger than carbon. Rein the horse back in. Is oxygen bigger than carbon?
No.
Okay.
Not effectively.
OChem Not at all. Gen Chem,
A little bit.
oxygen is smaller than carbon. Okay? So you have to be careful with size. Size does not change as far as we're concerned across the row in a periodic table. So when we're making our comparisons, we're saying we remove the hydrogen because we're looking for conjugate bases. Look at the atom, oxygen, carbon. Where are they? They're in a row. We're looking at what changes across that row. Size does not change, which means next rule, electronegativity. Okay? We can now compare the blue hydrogens between those two structures. Okay? So let's go through and erase that out. The hydrogen has been removed. We've called attention to it. We now have a negative oxygen. They both have the same charge. Oxygen versus oxygen. Do they have the same? Resonance is an incorrect answer. Do they have the same size? Yes. Do they have the same electronegativity? Yes. Because those are both yeses, I have no difference. I continue down my list, and the next one in my list is now I can evaluate resonance. Okay? And in that evaluation of resonance, what do I see? One does have delocalization and/or resonance, which means that structure becomes more stable. Because it is more stable as a conjugate base, that means
It's a stronger acid.
the original acid was the stronger acid. Okay? Kind of, sort of? What you have to be doing is thinking about those structures. If you aren't drawing out those structures, you're not doing this correctly. Okay? So, let's go through and take a look at how these rules could apply out to, say, an acid. If I'm looking at an acid, I want to evaluate the conjugate base. Why do I evaluate the conjugate base? Because that's where I see the electrons. I'm looking for a more stable A-. So what would I be looking at if I was looking to compare? Let's go ahead and just throw on another one. H will do C so we don't get confused with the B. If I was going to compare A and D with rule number 1, what am I looking for? Which of those would be the stronger acid if I was using rule 1 to explain it? Remember how it's drawn is going to be slightly different. Okay, so all we've got is what's, I don't know why I switched to the letter D. That was a bit silly. Sorry. Okay, what we've got drawn up there are kind of examples, general examples behind this. If I'm going to use rule 1 to distinguish between those, what would I be saying? They have different charges. Good. For one to be the stronger acid, what would I expect to see?
Different charge.
Okay, different charge. They have different charge. Which one's the stronger acid? Okay, different charge is not good because a charge can be different 2 directions. Okay, there we go. If I was going to look at these and use charge to evaluate these, the stronger acid is going to be the neutral conjugate base. Right? If I move to rule 2, the stronger acid will be whichever one is bigger. Rule 3. Which one's the stronger acid? The most electronegative. Rule 4, molecular effect size in quotes. What we're talking about again is where the electrons can exist. Okay? So when I move to a molecular effect of size, what I'm talking about is can those electrons exist across the molecule? How would I get the electrons to exist across the molecule? What would I be looking for the stronger acid? Okay. I'm just going to say more resonance. Okay. And really more resonance with the negative. Okay. Molecular effect electronegativity. Okay. This is the induction rule. What would I expect to see for induction? Okay. More induction. Okay. Or more negative atoms nearby. Why do they have to be nearby? Okay. The closer it is to it, the more likely there's an effect. Okay. I'm not going to move into 6 with the hybridization because I'm kind of out of space. Okay. So we now have ways to evaluate 2 different things based on their acid strengths. Cool. We've got rules to follow. Okay. And instead of just erasing everything, I'm now going to switch to bases. So we'll do B and D. How would I know which one was the stronger base? By looking at charge. The stronger base will be more charged is already going to become a problem, just like it was to begin with. What did you suggest?
More negative.
Our stronger base needs to be more negative. Okay. How about size? Smaller. Okay. How about electronegativity? The less electronegative. How about resonance? Less negative resonance. How about induction? Less induction. Anybody notice a trend here? They are exact opposites of each other. I wonder why that is. What's the definition of an acid? Proton donor, base, proton acceptor. What's the difference between a donor and an acceptor? They're opposites. You're using the exact same rules in the exact same sequence. Okay? You're changing your interpretation on them because the definition that you're asked to compare them at is changing. Make sense? Yes?
This may be a simple question, but how do we know if you're referring to the Lewis acid donor definitions or the Bronsted? Because I have it.
It's okay.
When you say acid, I think acceptor, not donor, which you just said.
Okay. So we did talk about that on Monday, and I fully expect to kind of explain this, but let's see if somebody else has this. When I say acid, what am I talking about? Bronsted-Lowry, always. Okay. I do not use the Lewis definition because it is too broad of a definition. Okay. So when I talk about acids and bases, I'm specifically talking about Bronsted acids and Bronsted bases. Okay. If I want to switch to a different reaction, say a nucleophile and an electrophile, really? There's a whole new level of new definitions to apply? No! It's the exact same rules. Nothing changes about it. All you have to do is acknowledge what is that molecule doing. Okay? If it's a Lewis acid, what must it do? Accept electrons. What is a Bronsted acid doing? Donating protons. How does it donate protons? By accepting electrons. They're one and the same. The spins behind them are slightly different. Okay, and that's it. We're still applying these exact same rules. Okay? For those of you hoping we don't have to cover these rules ever again, virtually every reaction, I will ask you, how do we compare the reactivities of things? And it will start with
What is the most acidic?
charge. And then it will move to size, electronegativity, resonance, induction. And then usually I stop and don't ask everybody to shout out the other ones. Okay? But that is how we're comparing the reactivity of different pieces. If you do not evaluate that, that is okay. You need to memorize a lot. So when people complain about OChem and being too much memorization, that is why. They didn't bother to actually learn how to apply the rules behind the system. Okay? Some of that is also just time. It's hard to apply those rules. Okay? So, if we looked at these reactions, could we predict which one of those was more likely?
Yes.
How?
Compare the list we just went over.
So we could try and do that, but both of those end up with charges on both sides.
Look at the pKa.
We could go back to 152 and use pKa's. What's the pKa for a carboxylic acid? Okay. Did you say what?
4 to 5.
We'll say 4.5. We'll just take the difference. pKa of water? 16. pKa of H3O plus? Negative 1.5. For those of you saying you don't have this memorized, this is going to be one of the points that we'll address here in a second. Okay. When we go through and get to the bottom one, we could go through and evaluate pKa's down here. This one is going to be something on the order of like -4. Okay, that's not one I would expect you to know. Okay. Which of those two reactions is most likely to proceed forwards? Top one or the bottom one? I think I heard someone mumble out the top one. Why is the top one more likely to proceed forwards? What was that?
It's less stronger than
The product that is produced is a less strong acid. Okay? You could go through and use your KEQs and your pKa's and all that fun, awesome stuff and do all that fun stuff with it if you really wanted to. Okay? Would either of these reactions produce a significant amount of product? No, why not? We're going to forming a stronger acid. Okay? Those pKa's are smaller on the right-hand side. That wasn't the question that was asked initially. It's which of these would progress more. Okay? If we look at the pKa's, we can make that decision right away. Which of those is the stronger acid? Benzoic acid, 4.5, or water, 16? Benzoic acid, are you laughing because I said benzoic acid? Yeah. Okay, so that's the benzoic thing and water. Which one's the stronger acid? The benzoic acid because lower pKa. Which means when I mix benzoic acid with water, what would I expect to happen as the most likely scenario? Benzoic acid should act as an acid. Which of those two reactions showed benzoic acid acting as an acid? The top one. Okay? So we can use pKa's up the yin-yang to explain where these things move. That's cool. That's fine. That's awesome. There's a little equation up there, which I don't actually think is going to be important because I don't think I asked the question in the smart work. KEQ equals 10 to the delta pKa, the difference in your pKa's. I don't really care about the KEQs and pKa's. Okay? You can use them to predict reactivity just like you could use that sequence of 5 things. What were those 5 things? Charge, size, electronegativity, resonance, and induction. Cool. We can use pKa's just as much, but that requires that you know the pKa of a carboxylic acid to be 4.5. How many of you knew that? Okay, one guy. Good job. Why do you know that?
It's just not in the book.
Cool, that's fine. You would also need to know the pKa of water. How many of you knew the pKa of water? That one's a little bit more surprising. And I would have assumed you'd known the pKa of water because you'd probably used it a lot in 152. But that's okay. Don't stress. Okay? Knowing pKa's can be helpful. It can allow you to go through and predict reactivities. It can allow you to predict if that reaction happens. There are some reactions that will be like, well, I wouldn't expect that to happen, but if you look at the pKa's, it does happen. Okay? In my opinion, those are reactions that I would memorize. Wouldn't bother to memorize the pKa. I would just bother to memorize that that reaction does something that I wouldn't have predicted it to do. Okay? That is now something I'll bother to memorize. I won't look at all the charge rules because it doesn't fit in that nice little bubble. Okay? This means we could pull out our reactions, KEQs, and oh man, all that good stuff. Okay? Ultimately, the big thing we need to get out of this is a big pKa is a weak acid, a small pKa is a strong acid. Does a big pKa mean it's a strong base? Okay, I saw some kind of head shakes no, which is really good. It does not mean it's a strong base. It means the conjugate base is a strong base. The pKa for methane, CH4, is somewhere on the order of 50. Can methane act as a base? What does it need to do to act as a base?
Lose the hydrogen.
What does it need to do to act as a base? What is the definition of a base? Accept a proton by
Losing.
donating electrons. Does that methane structure have electrons? No. So when we reference that conjugate base, what we're saying is if I look at the conjugate base of that structure, i.e. I remove a hydrogen, what do I now have? Electrons. That structure is now a really strong base. Why would that structure be a really strong base? I'll kind of accept because it started as a weak acid. I would argue there's something else that you should be looking at. Charge. Followed by size. It's one of the smallest elements we've got. It's one of the lowest electronegativities that we've got. Does it have any resonance? No. We've got a whole bunch of things contributing to why that structure becomes now a very strong base. Okay? So be careful with those memorization techniques because there's very often a word that ends up getting dropped out of it. In that memorization, a large pKa means a strong conjugate base. You have to remember that conjugate in that memorization. Okay, so pKa's, knowing them is a really, really good idea. Okay? That said, I never memorized pKa's, and I still survived. Okay? I have started to memorize some pKa's, okay, and it does become in handy with particular questions. You could probably just argue that you could have just memorized that one reaction instead of looking at the pKa's. But having a ballpark idea behind them is decent. Carboxylic acids come in about 4. That's what I've memorized, maybe 5. Alcohols are at 15. That sounds kind of familiar. That looks kind of like the pKa for water, because an alcohol is pretty much half water. Okay, so its reactivity is very similar. Okay, alkanes come in up at the 50 range. Alkenes are 40. Interesting. The alkene became a little bit more acidic. Why?
Increased S characteristic.
Increased S characteristic because the hybridization changed. Remember in the O carp? That's the O carp. It's a hybridization effect. Okay? Where it actually becomes important is not so much for the alkene, but for the alkyne. We get a really large drop in the pKa for the alkyne. It drops all the way down to 25. That does not make it an acid. Okay? Because our acid-base definition tends to hinge around water. It's kind of our center point, and water's pKa is 15. The alkyne is still significantly higher than that, so it's not an acid, but there are bases strong enough to deprotonate it. Okay? Phenols come in at 10. The amines are really, really tricky because when you look up the amine pKa, okay, I find it particularly irritating. You type in pKa for the amine, they tell you 35. No, that is not the pKa for an amine. What is that the pKa for? Or sorry, they tell you the pKa is 9. Sorry, when you look up an amine.
Amino acid?
Nope. That's actually where it becomes really, really important.
Is it just the ABrules?
When we're talking about the pKa for an amine and someone says 9, they're actually not referencing the amine, they're referencing the ammonium, the NH4 plus or NH3 plus connected out to the rest of that structure. Okay? That has a pKa of 9. If I want to look at a pKa, we're talking about it acting as an acid. If the amine acts as an acid, what does the structure look like? Define acid. Proton donor. If the amine acts as an acid, what needs to happen? It needs to donate a proton because that's the definition of an acid. What would it look like? The negative nitrogen. That would be what I would reference as a pKa for an amine. The pKa for that reaction is a 35. Okay? Why is that important? Is the amine particularly acidic? No, not at all. Is ammonium? Yeah. So you have to be careful when referencing the pKa for amines because there's really two possible states that they could be balancing from. I would argue they're labeling that incorrectly. We should be calling that the pKa for the ammonium and the pKa for the amine. Those are two very important things to distinguish, and it becomes extra important when you move into biochemistry. Okay? There's this effect here that I do kind of want to talk about. I know we're really short on time, called a leveling effect. Don't stress a whole lot about it, except acknowledge that you can't have an acid in solution that is stronger than the solution itself. Okay? Water's pKa is 15. Hydrochloric acid's pKa is like -4, -5. Okay? So if I'm going to run a reaction in a water-based solvent, I will not show HCl doing any acid-base chemistry. What I will be showing is the hydronium ion doing the acid-base chemistry. Why? When I add the HCl to the water, it reacts with the water to form hydronium. The hydronium is now the active species doing chemistry. This becomes hugely important in second semester, minor aspect in first semester. There's a bunch of stuff on thermodynamics and Gibbs free energy. We can quantify the crap out of a lot of it. We're not going to. Yay. Okay. Really what I wanted was apparently nowhere near where I thought it was. Okay, so I should just stop. We'll stop with this. This is 152, this picture. That's what you spent 152 doing. Okay. All the numbers were to make that. We will use that this semester.